That's the forward. The question we would like to address: are there loose threads in our understanding of the universe? First of all, we should find our place in the universe. And we live in a beautiful planet. It is actually a unique planet. There are a lot of pieces of rocks out there. They are either cold or too hot, completely inhospitable. Our is the most beautiful of all. Yes, it has its trouble, but it's beautiful. But then let's zoom out. We live in the galaxy, nicely protected from the threat of supermassive black holes in the center. We live in the outer arm of an ordinary spiral galaxy. Just one among hundreds of billions of galaxies in the universe. There is nothing special about the Milky Way. This is an image of the James Webb Space Telescope. The more you stare, the more you find galaxies, and they're all magnificent. So, the question is, how did it all begin? So the first loose thread is the beginning. We understood that as people, stars get born and die. The universe wasn't always there. It actually came to be. So this is a brief history of the universe. We know with certainty that it is about 14 billion of years old. It is very dense in the hydrogen, and there are billions of galaxies, and our sun and the Earth with it just came about 5 billion years ago, which is, in terms of the age of the universe, quite in the late time epoch. We also know that the universe is expanding. We got to know that roughly 100 years ago. It is expanding. It means it has to be very small at some point in the past. This is a very simple yet a very profound deduction that Georges Lemaitre made first. And because of the expansion, it had to be extremely small at some point in the past. And we call this a singularity. When scientists tell you that something is a singularity, it is a way to say that we don't understand it. So the first thing is everything started with a bang, but it is a loose thread. So, but we are here, I'm talking to you, so we exist, we are real. The second loose thread is about the composition. Now, matter got created very soon after the Big Bang, because by expansion, the universe, which initially is a very hot soup with primordial particles, cooled down pretty much like when you want to decrease the heat of a risotto, you span it on a wider surface. And thanks to that, stable atom can actually get created, and hydrogen get created from all the normal matter. However, when you make a count of what we call the cosmic pie, that essentially tells you all what is in the universe, well, actually, we found out that what is normal matter, stars, gas, galaxies, us, only count by 5%, barely, of the whole things that is in there. And something that is actually making us awake now is that the vast majority of matter, we don't know what it is, and we call it dark because it doesn't interact with light. Professor Vera Rubin, here with me a few years ago, was fundamental in actually making the evidence for dark matter. There is yet another component on which I'll come back a bit later. So, we don't know what is the major component of the universe, but as we said, we are here talking about it. So let's proceed and see what is the structure of the universe. That's another loose thread. It turned out that the universe started as super homogeneous. You have your soup, you stir it with a spoon, everything is homogeneous, but then by expansion it changed completely and it became strongly heterogeneous. And that's what we call the cosmic webs. There are filaments, clusters of galaxies, we call superclusters of galaxies, but there are also under dense region that we call voids. We actually don't know what it is. So that's a radical transformation. And because of the dark matter, what we understand is that, in principle, structure should form hierarchically. This word that we use in political science, we also use it in astronomy. Hierarchical means that the small structure form first, and then they coalesce together to form the biggest galaxy. Gravity is a non-democratic force. It gives much more to the rich. Nothing would have started if there wasn't a strong imbalance, unexplained, right at the beginning. Because thanks to the imbalance, matter gets accreted. If everything has the same power, nothing can evolve. So, is that really true? Actually, and that's really our work, we showed something very interesting that we still think about. Why is that? While the dark matter aggregates hierarchically, galaxies rebel against this diktat, and they actually form from the top. In this scientific plot, what you need to take home is that the biggest galaxies form at the beginning of time rather than at late time, which pose into crisis the whole cosmological model. It's good to have a crisis because this is food for thought and you can think about it. But there is a decoupling in the behavior of normal matter versus dark matter. So, as you can imagine, the final loose thread is the future. Are we able to predict? We make theoretical models of where are we going into the future? In '98, which is the same time I got my PhD, there was a catastrophic discovery. We said the universe is expanding. I blew a balloon and I can do this constantly. No, it seems it's expanding in acceleration. Essentially, it's ripping off. Now, it's like when you drive a car, if there is an acceleration, you need to assume there was an energy that gave the push. But in our standard model for particle physics, we do not have that energy. So we need to assume there is a form of dark energy, and I use one of my favorite figures in the Star Wars saga that really explain the concept. It's an energy that only has an effect on accelerated expansion of the universe. How bizarre is that? That got the Nobel Prize. We're still thinking about what that is. But if that is true, the ultimate destiny of the universe will be to become larger and larger very fast. What? We are actually trying to understand. I can, however, leave you by telling you what will certainly happen to our galaxy. So, as the universe proceeds in its time, we are at 14 billion years, but the more we look forward, stars will die, including our sun. The gas gets consumed. All the galaxies will dim, and we will live in a cemetery of stars, dead stars like black holes, neutron stars. Most importantly, in 3.5 billion of years, our galaxy will collide with the Andromeda galaxy. We can actually predict this quite correctly in terms of time because of the two velocities pointing to each other. 3.5 billion years, we have some time to get organized. Thank you very much.